Now, there are hazards and race conditions that you can end up designing into your endpoint device if you're not careful. Now, with multi-core, multi-threaded processors and operating systems, this is even more critical. So in order to avoid this, you really need to think like a driver or OS programmer, or at least have them work with you to define what your register set and hardware-software interaction model looks like. So an example of something you want to avoid is you don't want to have registers that when you read them cause a state change. So this can be an issue for example, when you have bridges or processors that do some prefetching. You would see this a lot in legacy PCI, for example. Also, you want to avoid reads causing state changes where you are packing multiple devices into a single D word. So for example, reading from a UART. Now this is a case where you can't avoid having a read sensitive device, because here you're going to be reading out of a FIFO, let's say a byte at a time. So you want to obviously avoid having multiple 8-bit registers packed into the same D word. And that's important because there are some processors that do not have a read per byte capability, especially embedded processors. Also, the byte lane selection is not available for prefetching, for example. So there are scenarios where it may be difficult to work around something like that. Now, I/O virtualization and the constructs being put into IOV, this is something that is good to understand, in that the techniques used in IOV will allow you to avoid a lot of these pitfalls. So these are things like, for example, having multiple views of the register space for different processors or processes. The impact on system performance of getting this wrong can actually be pretty significant, and that's why I'm bringing it up here, because poor control mechanisms can lead to a lot of major workarounds that impact performance and will make your software guys really hate you. Interrupt controller design. One of the issues you get into with SoC devices is that they're typically made by stitching a lot of IP blocks together. And as a result, it can sometimes be a last-minute decision about, gee, what do we do with all these interrupt sources? How do we deal with that? And a common practice is just to basically take them all and OR them together. And the problem with this is that software has to then go looking around to figure out, where did this interrupt source come from? So best practices are to employ a single read-only status register. So bring all of your devices into a big status register, 32-bit, 64-bit, that is centrally located, and then use that as a way to determine which IP block has generated that interrupt. So here you don't have to go and hunt around polling multiple registers. I mean, you always have the option of polling if, for example, if you don't want to use interrupts, then that register gives you a convenient place to go and poll. So when you're generating multiple interrupts, so these could be multiple messaged interrupts or hardwired interrupts, then it's convenient to have an enable or mask per bit per interrupt output. So if you were generating several, let's say 2 interrupt outputs, then you have an interrupt register per output to mask or enable the specific interrupt sources to pass through. Also, make sure it's possible to clear each interrupt source separately. You don't want to cause clearing of one interrupt to clear another interrupt. Make sure that you support INTX. This is the legacy interrupt mode, in addition to MSI or MSIX. WinXP, for example, and below do not support MSI or MSIX, only legacy interrupt. So this is an example of an interrupt controller. So here we have a single interrupt status register that combines all the interrupt sources into one convenient place to go and poll. And then there are a series of enable registers, one per interrupt output. And in this case, some of those interrupts are being forwarded to an MSI int_x generator, and then some of them are being forwarded to GPIO. Now some issues to consider with respect to scalability of your design and to be able to take it to future PCI Express generations. First of all, context switching latency is not going to get better. It's going to tend to get worse, or at best stay the same. So don't rely on fast interrupt handling to keep data moving in your system. Also, if possible, avoid interrupts. Use polling, for example. Rely on DMA with large scatter-gather lists. Remember that DMA is the way that you're going to get high throughput in your system. And scatter-gather lists that are able to ride out long interrupt latencies is going to help rather than big buffers. Assume that throughput and latency will both increase in future systems. So for example, you can have a host driver poll on semaphores that are based in host memory. Here you have the endpoint device write directly into host memory and maintain those semaphores. The hardware-software interaction model should be carefully chosen to be relatively insensitive to packet-level latency. And in fact, this is a good test. If your system is very sensitive to packet-level latency, for example, being behind layers of switches, then this is a sign of a poor hardware-software interaction model. Assume that interrupt latencies will be widely variable. And this is particularly a problem for isochronous data, for example, video. So here, rather than relying on large, deep buffers, for example, DDR memory buffers, it's better to rely on deep scatter-gather lists so that you can effectively launch and forget a series of scatter-gather processing that will be able to ride out very long latencies of servicing at the interrupt level. Also, you want to take advantage of the bidirectional nature of PCI Express. So that means avoiding internal buses like AHB and so on that are not bidirectional. Alternately, if you want to use something like AHB, then you want to separate the upstream and downstream buses so that you can feed the transaction layer independently. Well, that brings us to the end of the presentation. Thank you very much. I hope you've enjoyed it. Remember, for more information, to go to the Genome website. Here you'll find many resources to help you in your design, whether it's IP that you're looking for or chips for implementing endpoint devices. Thank you very much.